Hello friends, today we will cover the remaining topics that we have started discussing in our last tutorial. So if you haven't gone through my previous tutorial, I would request you to please have a look at it and do subscribe my channel. So today in this class, we will be continuing our discussions on skewness, Chebyshev's inequality theorem, what is long normal distribution, and what are the formulas for standardization and normalization, why we do standardization and normalizations. So these are the topics that we'll cover today. So having stated that, let's start. So we covered central limit theorem. Now let's see skewness. Now I was talking about skewness right here, left skew, right skew. What exactly are this particular terminologies? One more thing, guys, I wanted to mention, which I might have forgotten, is like if the population's mean is not known, right? So what we do, we draw out samples. This I have been repeatedly saying for the last three discussions, right? So this particular X bar of this particular sample, right, is also known as the point estimate of this population. So there are two terms, point estimate and another one is interval estimate. Now I will talk about interval estimate in my forthcoming videos, where I will talk about confidence intervals, hypothesis, what is null hypothesis, what is alternative hypothesis. So all these things we'll discuss. So for now, just keep in mind that this sample mean is also called the point estimate for this population, because based on this, we're estimating the population's mean or population's parameter. So that's why it is called as the point estimate. Point estimate. So sample mean is this one is the point estimate of the population mean. So please remember this. Okay. So this was all about central limit theorem. Now let's go to a new screen where I will discuss the skewness. Okay. So skewness is we want to understand the distribution of particular variable when we plot them in a graph. Let's say, so let's say the variable x, it may have various values, right? Let's say 1.1, 2.3, 4.4, again 2.6. Like this, it will have various values. When we plot them, it will take a shape, right? When we plot them in a particular graph, it will take a shape. Now the shape can be like this, or the shape can be like this, or the shape can be like this, right? It can take other shapes as well, but let's say we are considering this. So it can take any of these shapes. Now we know if it is taking this shape, it is nothing but normally distributed, right? What is the characteristics of a normally distribution, guys? Its mean, median, mode are at the highest peak. This point is the point where mean, median, mode are equal. And then if you divide this particular graph into two segments, both the sides will be symmetrical. So these are some of the characteristics I discussed in my previous class and just a few minutes back as well, right? Now, for this particular graph, mean is equal to mode is equal to median. Now for this graph, where you see the tail, this is the tail on the left hand side. You can remember by just you can remember which is what by just remembering these few points. The tail is this is also known as the tail. The tail is on the left hand side. For this one, the tail is on the right hand side. Okay, on the right side. So the graph is known as a right or left skewed based on the tail. Okay, so this you see this is looking like a tail, right? If you I'm giving you a very vague example. If you draw a cat or a dog, you will see they have a tail, right? Like similar to this or similar to this. right? So this is also kind of a tale. Think in that way. I know that I might sound foolish, but this is how we can remember if you want to. Okay. So this particular graph is known as left skewed. Left skewed. Wait. Okay. Since the tail is towards the left, this particular graph is right skewed. Skewness means elongation. It's continuing in this pattern. Okay. So this is left skewed. This is right skewed. This is also known as negative skewed. And this is also known as positive skewed. This you already know. This is normally distributed. Okay. Now, why it is important to know the distribution? What important role the skewness plays? Because if you see, if your data is not normally distributed, there are, as I just previously mentioned, a lot of the statistical techniques you cannot apply. So whenever you'll see a distribution like this or this, you will always try to transform this particular distribution similar to this. You will try to transform. When you will see the practical implementations, then you will see that how we are transforming any distribution to a normal, similar to a normal distribution or Gaussian distribution. Because if we transform, we'll get lots of advantages. We'll take, then the distribution will be normal. We can assume something. We can talk about their averages. We can talk about their symmetry. Lots of things we can calculate, and lots of assumptions and predictions we can make if our graph is normally distributed, right? So this is skewness. There are two types of skewness: right skewed, left skewed. Left skewed when your tail is on towards the left, and right skewed is when your tail is towards the right. It's as simple as that. And how we're drawing it based on the data that we have. Then the distribution of the data may be in any form. We don't know, right? In any form. So maybe some of the data points will be like this. Maybe some of them like this. We don't know, right? So this, if you see this pattern, then you know, okay, this is a skewed data. This is a skewed data. And based on the tail, you know what type of skewness we are dealing with. Now you may ask me, okay, Anupam, you have discussed about the skewness, and you told us about there may be data. What are the examples where in the real world we'll get this type of data distributions? Now let me give you some examples. Let me give you an examples of this type of skewness. So first of all, let me give you examples for a positive skewness. Let me go to some other screen. Okay, so a right skewed data. These are the examples. So if in interview someone asks you, okay, you have told me the skew, what is skewness, but can you give me some examples that which are rightly skewed data and which are left skewed data? Then you should be, able to answer them. So one of the examples may be movie ticket sales. Movie ticket sales. This may be one of the examples for a right skewed data. So let's say this is your sales, right? Let's say 1 million earnings, 2 million earnings. This is 10 million earnings. This is your 50K and something like that, right? So most of the earnings will be in this range. Most of the earnings will be in this range. Only few blockbusters will come in this range. Any blockbusters, right? Movies will come in this range. They will earn this many sales. and most of them will be falling in this category. So all the hits will fall in this category. Majority of them will fall in this category. Flops will be in this category, but few of them only will be in this category. And few of the movies are really blockbuster movies, right? So this is one of the examples of a right skewed data. One more example may be points scored in a difficult exam. This may be one more example, difficult exam. So let's say this is one graph, right? This is also, so points score in difficult exam. So normally, let's say this is 20, 30, and this is 70, this is 10, this is 5. So if it's a difficult exam, guys, so most of the students will be ranging, from 0 to 50, most of them. But only few excellent guys who can crack this exam will fall in this category. Will fall in this category, or less or greater than 75, right? They can pass with distinctions, or they can score more than 80, 90. So there will be few categories if it's a difficult exam, because not all students may be bright, you know. So most of them will fall in this category. So this is one of the examples of right skewed data. One more example, if I may give you, is the number of pet you own in your families. So pet ownership. This can also be an example of a right skewed data. Maybe this is the number of pets you may have in your house. So most of the population, or most of the family members will have maximum 3 to 4 pets, right? Average. Only few of them will have more than 5 or 6, or let's say 7, if they're very much in love with pets, maybe dogs, cats, right? So this may be an example of a right skewed data. Average, most of them will have, maybe 2 or 4 maximum. Only few will fall in this category, will have more than 5, or let's say 7. So this is also a right skewed data, right? So this is about right skewed. Now let me talk about left skewed. Let me go to other screen. Examples of left skewed data. So left skewed means this, right? This may be left skewed data. So one of the examples will be, if I take maybe same movie ticket sales as per day. Okay, so this can be like Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, again Monday. So you see, normally the average number of people who are earning, right, or who are doing business, they work on Monday and till Friday. And normally the sales of the ticket also will grow, during Fridays and Saturdays and Sundays, in the weekends normally, right? So the sales will be lesser in the weekdays compared to the weekends. So this data is a skewed data, and this is a left skewed. And this is the days, you say Monday, Tuesday, Wednesday. If you plot the graph with respect to the days, the earnings will be a left skewed data, where the data will be higher during Friday, during the weekends, than the weekdays. And again, after that, again it will go down. Again, it will be left skewed. right? So this can be one of the examples. One more example, let me change the color. One more example can be points scored in easy exams. So right skewed was points scored in difficult exam. This one is points scored in easy exams. So if I draw the graph, so most of the guys will be able to score good marks in an easy exam, right? Only a few who are below average will be, scoring lesser marks. Most of them will be, able to score good marks. So most of them will be in this range. This can be like 50, 30, 70, like that, 100. So in easy exams, everyone is supposed to pass, right? Only few of them who are below average or who haven't studied will score lesser marks. So they will fall in this category. So this is one example of left skewed data. Right. So these are the few things about skewness. Now, one important thing that I might have missed. So let me give it to you. So this is a left skewed, right? And this is a right skewed. Now here, let me just see one of the things. I might have covered it. Yeah, so here, this is the mode. This is the median. And this is the mean. So these are the measures of central tendency for a left skewed data. Okay, left skewed data. So mean will fall somewhere here. Median will fall somewhere here. Mode will be at the top. For the right skewed data, this is the mean mode. This is the mean, median, sorry. And this is the mean. So mean is towards the right skewed. And in this case, mean is towards the left skewed. This will be the half of the data. This will be the half of the data average, right? So this and this, so this and this. So here will be the mean for right skewed. Here will be the mean for left skewed. So just to make you understand where is our central measure of tendency in terms of skewness, where they lies. So this is all about skewness, where I discussed what skewness is, what are the types of skewness, and what are the examples of the skewness types. Now we covered central limit. Okay, so we covered these two topics. Now I will talk about Chebyshev's inequality theorem. So Chebyshev's inequality theorem is also important, guys. So what it says is, let me go down. I can explain here also. Okay. So you have discussed. No, let me go to the some other screen. Never mind. Let me create one. I write it here. Chebyshev's inequality theorem. So what it says, guys, is normally in real scenarios, a random variable might not follow a Gaussian distribution, right? It might not follow a bell curve, maybe, as we saw in our previous case, right? the skewness. It is not following a bell curve. So many times it might happen that a random variables distribution may not following a Gaussian distribution. So what it doesn't, what will happen if it doesn't follow a Gaussian distribution? We have our formula, right? What was the empirical formula? 68%, 95%, 99.7%. This was the empirical formula for Gaussian distribution. What it says? It says Gaussian distribution or normal distribution, both are same thing, guys. What it says is 68% of the data points lie between first standard deviation and its mean, right? 68% of data will fall in this category. 95% of the data will fall between mean, mu, and second standard deviation. And 99% of the data will fall between third standard deviation and its mean. So this was all about empirical formula for Gaussian distribution. This we have discussed in our previous tutorial. If you haven't gone through that tutorial, guys, I would request you to please go back to those tutorials. And I am preparing these videos in sequence so that if you know one of them, then it will be easier for you to understand the next. Right. So when I'm talking about the empirical formula, you should know what exactly I'm talking of. So if you haven't visited or if you don't know about this empirical formula, please go back and visit that tutorial. Okay, so now let's say most of the times our distribution of the sample, a random variable may not follow this Gaussian distribution. So what will be the empirical formula for this? It is defined by Chebyshev's inequality theorem. I don't know whether I'm pronouncing it correctly, but so far as I know, it's Chebyshev's inequality theorem. What it says is the proportion of the area that lie between its mean and standard deviation, right? Sorry, its mean and standard deviation is given by this particular formula. Mu plus k standard deviation. It should be greater than 1 minus 1 by k square, where k is nothing but it's a range of standard deviations. They are the ranges of standard deviations. Okay, so this is the Chebyshev's inequality theorem. So for k is equal to 2 or k is equal to 3, how will you calculate? Let's say for k is equal to 2, if it is defined by meaning second standard deviation. Okay, so the probability of the data falling between its mean and second standard deviation will be given by this formula, right? 1 minus 1 by k square. So k square, 2 square is 4. So nothing but 3 by 4. So nothing but 75%, we can say. So 75% of the data points will fall under its mean and second standard deviation. This is what our Chebyshev's inequality theorem says if that particular distribution is not a Gaussian distribution. So in that case, 75% of our data points will fall between its second standard deviation and its mean. So similarly, if k is equal to 3, so let's say p probability is standard. So probability of the data falling between its mean and third standard deviation is what? If you calculate 1 minus 1 divided by k square, so it's 9, right? K square is 9. So it is nothing but 8 by 9, meaning 89% approximately. So 89% of the data points, 89% of the data points will fall under a distribution where it is between mu and third standard deviation. So this is what Chebyshev's inequality theorem states. Okay, so this was all about Chebyshev's inequality theorem. When we can define the area, okay, what is the area that is been covered by its and between the standard deviation and the mean? Because In Gaussian distribution is very easy, we know already. But what if it is not following the Gaussian distribution? So maybe it is like this, or maybe it is like this. In that case, how you will define how much area? So that is been done with this particular theorem. So 75%, 89%. Just remember this: 75% of the data points will be between second standard deviation and its mean. 89% of the data points will be between its third standard deviation and its mean. Okay. So this is all about Chebyshev's inequality theorem. So we covered this also. So this is also covered, and log normal distribution. Okay, so I will also discuss about log normal distribution. So log normal distribution, guys, just give me one sec. Move to the other screen. Make log normal distribution. I will talk about different distributions, guys, for a random variable. A random variable can take any distributions. It can be normal distribution, it can be log normal distribution, it can be, example of a binomial distribution or a Poisson distribution of a Pareto distribution. It can be of any type. Okay, but our goal will be to make it into standard normal distribution. So there will be various transformations like we call normally box-Cox transformations, where we transform our variable into random standard normal or normal distributed. So I will cover all these points, but not today. Okay, I will cover each and everything. Don't worry. So what actually is the log normal distributions? So it says that any random variable x is supposed to follow a log normal distribution if the log of this particular variable x is following a standard distribution or a Gaussian distribution with mean mu and standard deviation sigma. Again, I'm repeating, guys, a random variable. So this is nothing but a random variable. Random variable. So a random variable x is said to follow a log normal distribution if log of that particular variable x is following a standard distribution or a Gaussian distribution. Okay, with mean mu and standard deviation sigma. So let's say I have an x and there are various values like 2.5, 3, 7.9, something like that. Okay, it will say to follow this distribution if you take a log of this. So log of, let's say, 2.5, let's say this is another variable you created, which is ln x. So you take the log of these variables, a log of 3, let's say, a log of 4.5, whatever values are there in present, log of 7.9. If you get this variable, new variable, and you just take a logarithmic of these variables and you plot them, it will follow a normal distribution. Then you can say that this x is a log normal distribution. Normally, the graph of a log normal distribution is basically right skewed. So it is something like this. Now you know what is right skewed and left skewed, right? As I taught you. So normally, distribution of a random variable x, a log normal distribution is something like this. It is a right skewed. Okay. Now the examples I've already given you, right? What can be an example of right skewed? So log normal distribution, if say someone asks you, okay, give an example of a log normal distribution, immediately you know log normal distribution nothing but right skewed. So what are the examples in right skewed? So you give them the examples, right? So this is all about log normal distribution, guys. Now, what is the last topic that is remained? Is standardization. So this is actually, guys, very important. Standardization. I was also discussing standardization last class, if you remember, right? Why it was important, right? If we, let's say we have, again, let me give you a heads up. Let's say we have features x1, x2, x3, x4, and so on. If you want to compare these variables, and let's say these variables are in different scale. By different scale, I mean, let's say this is age, this is height, this is weight, right? This is income. Age is a number. Weight, height, it's in years, right? It's in years. Years is a scale of this age. Height, it may be in centimeters. Weight, it can be in kilos. Income, it can be in dollar, it can be any unit, right? So how you will compare these values? We cannot, because their scales are different, right? It is in years, it is in centimeters, it is in kg, it may be in dollars. You don't know. So how will compare these variables? How you want to, if you someone say, okay, find out the relationship between these variables, how you will know? You cannot compare them, right? So for comparing them, you need to bring them down in a particular unit scale. All of them should be in a same scale. Only then you can compare them. So that is done, that is been done with the help of either standardization or normalization. This is standardization or normalization, and this is very important. Also, you see why it is important. If you can bring down bring down the values, okay, to one scale, it will be easier to understand the relationship. If it is easier to understand the relationship, it is easier to build a model. It is easier to find out, okay, which features are important, which features are not important, which features are directly related with the target variable, which outcome, okay, or what are the features which are interrelated with each other, finding the multicollinearity. I will talk about what is multicollinearity and all when I cover the algorithms. But for now, just remember this thing. What is how we can find out the relationship between internal features like this x1 and x2. Let's say x1, x2, and x3 are internally related. They are influenced by each other. So in model building, I will not consider x1, x2, x3. I will just consider one of them only. Why I will look at three? So all this study we can do easily if you bring down the scale and if they are in different scales. That's how important is standardization normalization. What is the difference between standardization and normalization? Both are doing the same thing. The only difference is normalization will bring down the scale between 0 to 1. This is the scale. The values will range from 0 till 1 when you do the normalization. And when you do the normal standardization, so the value will range from -1 to 1 when you do the standardization. So you know the formula for standardization, right? Standardization was given by z equal to x minus mu divided by sigma. This was the formula we studied in our last discussion, last tutorial. Again, guys, if you haven't gone through my last tutorial, please, I request you to go through that. And what is normalization? So normalization is calculated as, let's say, x of norm is equal to x minus x of mean divided by, let me rub this, divided by, sorry, x max minus x of mean. This one I already discussed, right? For this one, let's say you have values like 4, x is a variable, 4, 6, 3, 2, 1, something like that. So you know how you calculate x norm? X norm will look for this value, what it will be? X meaning 4 minus x mean. What is the minimum? 1. Max, what is the maximum? 6 minus x mean. What is the minimum? 1. So 5 divided by 5. Sorry, 3 divided by 5. Whatever value, it will be ranging between 0 to 1, right? So it will have this value. Again, 6. So 6 minus, what is x mean? 1. What is x max? 6 minus x mean? 1. So 5 by 5. So it will be some value. So in this way, it will range between 0 to 1. Now you will ask me, okay, Anupam, tell me where we use this. One we have seen, right, for standardization. In normalization, what is the right example for normalization? So this can be done in image processing, guys. In image processing, you know, let's say 0 to 255. So you know the color combinations. You know that all our colors like RGB falls in this category, in this range. If you have a R value of, let's say, within this range, Z value of something within this range, and B value of something within this range, you can define a color. Any color can be defined with these three values. right? So 0 to 250. So in the case of image processing, which I will cover also, not in this machine learning series, but maybe when I start my deep learning series, I will start there also. So we'll get to know there how important is a normalization. You can even use normalization here also in normal machine learning, depending on what actually the problem statement is, what the problem you're dealing with. You can use either standardization or you can either use normalization. Doesn't matter. You can even check your results with doing by standardization and doing by normalization, and you can compare which is better. And based on it, you can choose whether standardization is helping you or normalization. But end goal is both of them are trying to do the same thing, guys. Both of them are trying to bring down the scale to one particular scale for all the variables in hand. Okay, this is all about normalization. So with this, guys, I am ending this tutorial. I hope I have covered quite a few topics today, and these are all the parts of basic statistics. I will take one more session on basic statistics. I will cover a few important points, and then straight away I will jump to our machine learning core concepts. Okay, and then also I need to cover something called pandas, numpy, through which you will be able to do your hands-on. So there are lots of things ahead, guys. Please be patient with me. I will be covering them in sequence. And yeah, that's it. So keep learning, keep shining. And also do subscribe my channel. If you find this video valuable to you, please like this video. And I really need your support, guys. Please subscribe the channel, share it with your friends, colleagues, or whoever want to learn something. And I will be happy to help. Thank you.